We talked before about efficiency, where efficiency is the radiated power divided by the total power supplied to the antenna, which is the radiated power plus the power dissipated as loss. Now, one way to think about this is your antenna is always going to be connected to a system, and it's always going to have terminals. And so the antenna, after those terminals have a current going into them. They have a voltage defined on them. So that means that the antenna can be represented as an impedance. ZA, and A is for antenna. But we can break that down even more and say, well, we've got this voltage and this current, cool, and that breaks down into some reactance that's associated with the antenna structure, a resistance for however much power is being dissipated to radiation, and a resistance for loss. Then if you write this down that way, then you can say, well, the power radiated by the antenna is just 1/2 magnitude I squared, assuming we're in phasor mode, times the radiation resistance. And the power dissipated as heat in the antenna, the power that's lost, is 1/2 I squared times R loss, which means that now we can write the efficiency in terms of those resistances, not as those powers. And that's great because now it doesn't depend on the current or voltage that's applied to the antenna. The efficiency in this expression is an intrinsic property of the antenna, not dependent on however it's being excited. We like that. The reason I'm bringing up radiation efficiency now is I want to talk to you about different types of antennas and what their advantages and disadvantages are. Oh, actually, I should back up. I should tell you one more thing. There's one more thing that you need to know about radiation efficiency, and that's how to calculate it. Remember that we have one other way of finding the radiated power. The radiated power is also equal to a flux integral of the Poynting vector over any surface that encloses the antenna. Now, using these two facts, if you know the Poynting vector from the antenna, you can find the radiated power, which means that you can find the radiation resistance as long as you know the current at the antenna terminals. How does this all come into play in reality? Let's go back to talking about the Hertzian dipole. Now, the thing about a Hertzian dipole is it's not actually a physically realizable antenna. Because if I were to plot the amplitude of the current along its length, if I made this a little graph where this is an axis of amps and this is the antenna length, the current on this antenna looks like this. It is constant. That is not a realizable current distribution on an antenna. The reason for that is current has to go to 0. at an open circuit. And the ends of the antenna are definitely open circuits, so the current has to go to 0 at the ends of the antenna. There's nowhere else for the charges to go. We can't have charge building up there because we're talking about steady state time harmonic operation. So if this is going to be a time harmonic situation, the current has to go to 0 at the end. All right. The closest realistic thing that we can get to a Hertzian dipole is a short dipole. Now, if I draw that same current plot for the short dipole, its current distribution looks more triangular. And here's why. On a transmission line, see, it all comes together in the end, that is open circuited, the current goes to 0 at the end, and you get a current standing wave that looks like this. And on the negative wire, your current standing wave is doing the same thing but with opposite polarity. So this current is going, the current on the upper conductor is going to the left, the current on the lower conductor is going to the right. Now imagine that you just bent your transmission line here and folded these little open ends out a little bit. The current distribution you got now is that same standing wave on the transmission line with just the very ends of that sinusoid sort of exposed to the air on the outside of the antenna. The interesting thing about this is now these currents go the same way because the current on this upper conductor follows along the direction of this arrow and goes up. And the current on the lower part of the conductor, remember this is the end, it's going to go up also. So they're oppositely directed on the transmission line, but because we fold the top wire up and the bottom wire down, they are co-directed on the body of the antenna, and that's what allows them to radiate. But because they are the very last bit, they're the very last little slice of this sinusoid, and for small values of x, sine x is approximately equal to x, we end up with this linear shape on each half of the antenna and a triangle shape for the current distribution as a whole on the short dipole. Now this means that the short dipole actually has less radiation resistance than the Hertzian dipole. Remember, the Hertzian dipole is not actually realizable, so that doesn't matter quite so much, but we got 80 pi squared length over the wavelength squared for a Hertzian dipole. But the radiation resistance of a short dipole is only 20 pi squared times the length over lambda squared. Now, a short dipole, you'll see different rules of thumb about this, but for a short dipole, that means that the length is probably less than 1/10 of a wavelength. Otherwise, the approximations that we make to get to this radiation resistance expression don't apply. So how could we get some of that radiation resistance back? The clue is actually in the current distributions. There is less area under this current distribution than there is under the Hertzian dipole one. And if you remember what I said about the far field radiation pattern being a Fourier transform, that means that the total area under this current distribution determines the amount of power that is going to be able to be radiated by your antenna. So if you want to radiate more power, you need a current distribution with more area under it. And that's how we get to the half wavelength dipole. That thing I just said was sort of a really conceptual, hand-wavy statement of Parseval's theorem, in case you want to follow along with the mathematical justification of things. So, half wavelength dipole. Let's go back to our transmission line. What if we start with a transmission line? We've got a standing wave because it's open-ended. So this current's going that way, and this current's going that way. And then we cut it right here, a quarter wavelength away from the end, and we fold up a quarter wavelength on the top and a quarter wavelength on the bottom. We just fold that up. Now I've got current on the top going like that, current on the bottom going like that. And my antenna current distribution looks like one single lump of a sinusoid. One half period. And that works because the length of this antenna is half a wavelength. Why does this happen the way it does? Because of standing waves. Because current and voltage are also waves, just like the electric and magnetic fields are, and they also prefer sinusoidal shapes. So when you make a standing wave, you're going to get a sinusoid as long as your excitation is itself time harmonic. Sinusoids just give you more sinusoids. So the half wavelength dipole has more area under the current curve, and as a result, it gets you more radiation resistance. The radiation resistance for a half wavelength dipole is 73 ohms. Now, if you have an actual half wavelength dipole, the input impedance of the antenna is 73 plus J 42 ohms for an actual half wavelength dipole. So actually most half wavelength dipoles are actually about 0.48 wavelengths. Depends on the wire thickness. Because if you make it a little bit shorter, you reduce the inductance until you can get a purely real input impedance, which makes the antenna easier to match and easier to deliver power to. So, as you might be gathering from this, efficiency is higher if the radiation resistance is higher. It's also higher if the loss resistance is lower, but there's only so much you can do about that with realistic materials. So, in general, we'd like to have a higher radiation resistance, and that is related to the antenna size and the current distribution. Why don't we just always use half wavelength dipoles then? Well, think about it this way. The wavelength at 300 megahertz is 1 meter. What's the wavelength at 30 megahertz? What is it at 3 megahertz? There comes a point where a half wavelength dipole is not physically practical, depending on what your application is. If you're not going to install it in a stationary location where you'll never ever have to move it again and you have a lot of land all to yourself, maybe a half wavelength dipole is not a good idea as you get down really low in frequency.